A few elements help surfers generate speed. For example, gravity pushes them down when they drop into a wave. Also, when they engage their rails, water hits the bottom of the surfboard and gets propelled towards the tail, which helps the surfer move up and forwards on the wave. Both of these are subjects of other courses on our online coaching platform, so make sure you check the link below for full courses on how to generate more speed on a surfboard. In this video, we'll focus mostly on how surfers use a technique commonly referred to as pumping in order to generate speed. Pumping is the act of surfing up and down on the face of the wave in a smooth flowing motion. Before getting technical, the first thing that is essential to understand is the type of line experienced surfers draw to generate speed. If you look at videos of experienced surfers, you'll notice that they use a lot of the wave's face when pumping, and then usually come back up to the top third. If they need speed, they don't ride further down the bottom of the wave into the flats, as they know they can easily lose momentum there. Also, they don't just wiggle in the middle. If they did this, they wouldn't benefit from good propulsion during their bottom turn as they set their rail. Neither would they gain extra speed as they drop back down. So the first thing to notice is that surfers usually pump by using lots of the wave's face and then often come back up to the top third. Another important thing to notice is that the line they draw is close to the pocket, also called the curl. Because the wave is steeper in this area, they can get more acceleration. Experienced surfers don't pump far out on the shoulder or very low down on the flats. The art of generating speed is done by moving to precise parts of the wave while shifting your body weight at specific times. It isn't just about pumping up and down in the right area of the wave. You need to know when to compress and when to decompress your body to maximise your acceleration. Look at advanced surfers as they start going back up towards the face. They unbend their knees, stand high, and throw their arms towards the direction they want to go to. Once they've gone up the wave, their board starts turning back down towards the bottom of the wave. At this moment, they bend their knees and compress their chest down towards the front knee. If you skateboard, think of when you want to drop down a quarter pipe. You need to lean your upper body down and forwards to let gravity push you down the ramp. Understanding the physics of pumping can give you some key insights on what needs to change in your technique. Did you ever wonder how skateboarders can start from the bottom of a half pipe and basically pump themselves higher and higher on the ramp? In theory, shouldn't a skater dropping in on a half pipe get no higher than where he was on the other side of the ramp? It would make sense to think this way, making a comparison to a pendulum, which will never get higher than its starting point once released. During the drop, all the gravitational potential energy converts into kinetic energy, and then the kinetic energy gets converted back to gravitational energy on the other side. If anything, the skater should go lower on the other side when considering friction from the wheels and air resistance. Yet we've all seen professionals start from the top of the half pipe and project themselves many feet up in the air to do impressive maneuvers. Learning how to build this momentum on a skate ramp can give you more understanding on how pumping in the water works, as a wave has a similar shape to a quarter pipe. Consider the following as a hypothesis that makes a lot of sense in practical terms, but has not been researched fully in the waves to our knowledge. We do apologise if the physics aren't 100% correct, and we understand skateboarding and surfing are different. We'd like to thank Nick Drachman, PhD student in physics at Brown University, for his article on the physics of vert skating. The following explanations are based on his work, and we've put a link in our description if you'd like to learn more on how he came to his conclusions. Okay, so how do pro skateboarders seem to magically defy the laws of conservation of energy? The answer has to do with the conservation of angular momentum. L being the angular momentum of an object, I being its momentum of inertia, and omega being the angular velocity. In the absence of any applied torque, L remains constant. This means that if you can decrease I, then omega has to increase to compensate. This might sound complicated, so let us simplify the best way we can. First, what is angular momentum exactly? Momentum equals the mass times the velocity of an object going straight. So angular momentum means the weight and velocity of a rotating object. One thing to understand here is the momentum of the object going forward on a straight line compared to an object that is rotating around in a circle are calculated differently. Think about it. If you are riding a skateboard on a straight line and push yourself forward, you will gain speed because of the push. If you are on a straight road, you will slowly lose speed because of the friction and air resistance, unless you push yourself forward again. Your momentum here would equal your weight times your velocity. To increase your velocity on a straight line, you'd have to somehow reduce your weight all of a sudden, which isn't possible. If you weigh 70 kilograms, you weigh 70 kilograms and this won't change in an instant. But when someone goes up and down a half pipe or on a wave, they aren't going to go in a straight line. They're actually rotating. Imagine a skater here. He isn't going on a straight line. In fact, you can imagine his line being a quarter of a circle. Therefore, a skateboarder riding in a particular part of the halfpipe is like a rotating object, and his momentum should be calculated with the equation L equals I times omega, and not momentum equals mass times velocity. L is the skateboarder's angular momentum as he rides this section of the pipe, and omega is his angular velocity. Increasing his angular velocity translates into moving faster around this section. So if we want to increase omega, we need to decrease I. I is the moment of inertia. It can be thought as a measure of how difficult it is to get something to rotate. Think about the playground game tetherball. The equipment consists of a stationary metal pole from which is hung a ball from a rope. Now imagine trying to swing a 15 kilogram rock instead of a ball. It would obviously be harder to swing a rock around. Okay, now let's compare two more scenarios. If you were trying to swing around a 15 kilogram rock when the rope was 1 meter long, compared to swinging the same 15 kilogram rock around on a 5 meter rope, it's going to take more effort to swing the rock on a longer rope. With these examples, you can now understand how I, the moment of inertia, depends on the weight and the radius of rotation. The moment of inertia, again in other words, how hard it is to get an object to rotate, can be reduced significantly by shortening the radius of rotation. This is what skaters do when they pump. Let's take the example of a 70 kilogram skater riding towards the bottom of the ramp. As we've said before, he can't suddenly change his mass to gain velocity. What he can change though is his centre of mass, which is done by pumping. If you compress your knees down, your centre of mass would be about here. If you decompress by extending your body, your centre of mass would move up about here. Now imagine these 2 points are like the rocks spinning around in our previous example using the tetherball playground game. By starting with bent knees and then extending them as he goes up through the transition of the ramp, the skateboarder brings his centre of mass closer to the axis of rotation. As you can see, the first radius is longer than the second one. A smaller radius reduces the moment of inertia and therefore increases the skater's angular velocity. This projects him up the ramp with more speed than if he would have kept his knees bent. Here's what we think are the main lessons for your surfing. The extension of the body when turning up on the face of the wave works in very similar ways to skating on a ramp. Surfers are also drawing a circle as they turn, although they are going up diagonally when they generate speed, compared to the skater going straight up the ramp. When experienced surfers go down the bottom of the wave, they compress their knees down. As they turn back up towards the top of the wave, they decompress by extending their body and throwing their arms towards where they want to go. As they do so, they are bringing the centre of mass closer to the axis of rotation. Again, the moment of inertia is reduced and the surfer gains velocity. Depending on your level, this knowledge could help you improve your technique in different ways. One of the most common mistakes is to mistime the extension of the body. There is a specific time to extend the body when you start turning back towards the face of the wave. As you can notice here, the surfer's centre of mass does not get closer to the axis of rotation because there's no extension of the body. Another misconception is that extending and throwing the arms forward creates drive when surfing in a straight line on a wave. It won't work unless the surfer is turning back towards the top of the wave. Here the surfer throws his arm after turning, once going straight up the top of the wave. Therefore, he doesn't gain extra momentum by throwing his arms forward here. Think about if you were riding a skateboard in a straight line. Would extending and throwing your arms forward help you accelerate? It really wouldn't have much effect. More experienced surfers, at what we call level 2.2, are often developing techniques such as bottom turns, cutbacks, top turns, floaters, etc. They can pump up and down the wave's face, but more advanced surfers seem to be able to generate more speed than them. From what we have seen in our coaching retreats, there is usually room for improvement in how they set their rail in the water when bottom turning, in order to get more drive up and forward. The other element that is commonly underestimated by students of this level is just how much extension and throw advanced surfers actually do. The more the centre of mass moves towards the axis of rotation, the more acceleration the surfer gets. By looking at videos of their surfing, they often realise they could extend more and throw their arms further forward to gain more speed, and make sections they once thought they weren't able to make. Generating speed is huge. There are lots of other elements you can learn on our online coaching platform. Click on the link below to learn more about the use of your rails, gaining speed with gravity, adjusting your position on the wave, choosing the proper surf equipment to maximise your speed, and more.